Assalamu alaikum. This is Syed Qudratullah. Today I am going to talk about my final year project, which is genetic algorithm based multi-objective optimal power flow for improving the power system performance. So this project is supervised by engineer Mohammad Fawaz Sheikh. The project overview. The optimal power flow involves solving a set of equations that describe the electrical behavior of a power system. These equations model the flow of electric power from generation to loads, taking into account the voltage, the transmission line losses, voltage constant, and other system limitations. The problem statement the problem statement is to reduce the generation cost of a power system and to improve the power system reliability, also reducing the greenhouse gas emission. So these are our aims and objectives. The first objective of our project is to minimize the generation fuel cost. The second objective is to reduce the active power losses, and the third objective is to maintain the voltage level, means to improve the power system voltages. So this is our methodology. First, the literature review, then the problem analysis, then problem solution, then modeling in PSSC or MATLAB, then testing, and then implementation. So here are some related research articles. You can see different techniques have been used for the optimal power flow. So this is the multi-objective end-to-end optimization, improved multi-objective optimal particle swarm optimization, hybrid firefly, PSO. You can see different cost values here. Shows that how the fuel cost is optimized, and you can see the values change here for each technique. So means everyone try to reduce the optimize the voltage, the generation cost. You can see. So these are the different techniques that have been used so far. So now here we have the 5 bus bar system on MATLAB. So we have taken the 5 bus bar data. For that we will check our data first of all. So we implemented the 5 bus bar system here, you can see on MATLAB. So the purpose of implementing this that system is to check the data that we have taken is valid or not. So we will do load flow for that purpose. So first we implemented the 5 bus bar system here on MATLAB. So then we run the program. You can see here the voltages level here shows that the load flow is done successfully. So then we move forward going with the same data. So this is again the same data of the 5 bus bar system. We implemented the 5 bus bar system on PSSC software. You can see then we did the load flow again to check that the results that we have taken from MATLAB is correct or not. So again we did the load flow. You can see here the voltages, they are similar to the data that we have get from the MATLAB case of 5 bus bar system. So you can see this. This shows that the data that we have taken for the 5 bus bar is correct. So we can move further for the genetic algorithm for the 5 bus bar system. So now this is the generated cost coefficients. You can see here there are three constants. Means A in blue shows that the additional cost of the a power system. Then this is the quadratic relation with the power, and then B multiplied with power. This is linear. You can see in the graph. So this should be shows that the variable cost of the generation, and then in the last C shows that the constant. So here you can see that is a constant, and it is the fixed cost of the generation. So this equation is very much important while going for the genetic algorithm code. So you need to work on this equation much more, because you need to find the A, B and C. Then you will calculate the generation cost. So now we have the 5 bus bar system. Here you can see this is the SLD of the 5 bus bar system. So the base case we need here, we did we run the base case in PSSC software. Here you can see we get the results. So you can see here the cost, that is 429.9 per hour, and also the total losses you can see 6.14 megawatt. Here you can see also the voltages are divided from first to fifth bus bar. You can see these are very divided. So this is our base case. Moving with this case, this is our case number 1. You can see we did the optimization. Here you can see the voltage level has been improved. Also you can see the blue shows that the base case, we will compare with the base case, our optimized case. So you can see the cost is reduced now to $422.08 per hour. Also you can see the total losses, that is 6.14 megawatt reduces to 5.32 megawatt. This is how we use the generator cost coefficients, the A, B and C. You can see here we use these coefficients, and then we calculated the generation cost. This is our total cost in Pakistan rupees PKR, and this is our total cost in dollar per hour. So this is the 5 bus bar system, and we have calculated the generation cost, that is $422.08 per hour. This is our case number 2. Actually we put the DG on bus number 5. Here you can see actually we don't know the exact location of DG. That could be here or here. So we will go one by one to check on this position, that how much we reducing the cost and voltages we will improve or reduce the total losses. So first we have taken the DG on bus number 5. So this shows that the result, the base case result is of 429.9 is reduced to 409, and then the voltages, you can see the voltages improved to 1. And here you can see 0.95 improved to 0.97. Also here you can see on bus number 4 and 5. Similarly, the total loss is also reduced to 2.85 megawatt. This is our DG on bus number 5. Then we again put the DG on bus number 4. Case 3 shows that the DG is on bus number 4. So this is the cost of a base case, and that is the optimized cost. Means when we put the DG on when we put the DG on bus number 4, so this is the cost, $415.18 per hour. Also the losses, you can see reach to 2.33 megawatt. Here you can see the voltage level is also improved here with DG at bus number 4. You can see these are the deviate voltages from 1 to bus 5. So now we have case number 4 where we put the DG on bus number 3. Here you can see. So this shows that we don't know the exact location. Means we are going for each location here on bus number 5, then 4, then now we have a location of DG here on bus number 3. We will see the results. Here you can see the cost is reduced, not that much as in previous cases. Also the losses are reduced to 4.4, 2.42. Here the voltages are improved very well. You can see here in the figure. So now this is the comparative analysis of our study. Here you can see we have the base case and the cost of generation cost, and then the losses in the base case. Here you can see. Then we have case number 1 when there was no DG, we only optimize. You can see this orange line shows that the optimized value of voltages. This is the cost then we get, and also the losses. Then again we put the DG on bus number 5. You can see here. Then the loss is reduced to 2.8, and then we another case DG at bus number 4. The loss is reduced to 2.33, and then we put the DG at bus number 3. The cost is reduced, and also the voltages, the total line losses reduces. So the best case that we picked from our analysis is DG at bus number 4, case number 3. Here you can see the voltages are improved compared to the base case. Also the line losses reduces, and the cost is 415, which is reduced compared to the base case. So we have the cost reduction and losses reduction. We can also say that we have improved the voltage level, because you can see the voltages are much deviated in base case. This line shows that the light blue, that the voltages is improved. So now after the 5 bus bar system, we move for the 30 bus bar system. Means we extended our 5 bus bar system to 30 bus bar system. Again we have the 30 bus bar system base case, which we have taken from the PSSC results. You can see the voltages are very much deviated. Here you can see the cost is $914.36 per hour. Also the total losses are 13.52 megawatt. So this is how genetic algorithm works. Actually it try to find the best fitness value with the generations here, and it's reached to good fitness value, you can say. Then it gives the result. So this is the first time when we try to optimize for the cost, and you can see here the voltages level have been improved here. Previously in base case, you can see here, and these voltages are much deviated from bus 1 to 30, and when we try to optimize it, the voltages level is improved now, and the cost also, which was 914.36, is reduced to $8 to $1.85 per hour. You can see the transmission losses have been increased. So this is the only thing that here you can see is the losses increased, but the voltages are improved and the cost is reduced. Then again we put the DG at bus number 14. Then we have the result. Here you can see there's $782 per hour. This is the base case cost. Also the line loss, total losses of the base case, you can see reduced to 12.7, and also you can see the changes of the voltages that is being improved. Here you can see when we put the DG at bus number 14. Then we put another DG on bus number 18. You can see here we have the result here in black for the voltages when we put the DG at bus number 18. So this is improved when we put the DG at bus number 14. The orange shows that the voltages level, and then we put the DG at bus number 18. So this is much more improved than the previous case. Also the cost is reduced to 760 and the voltages are now 12 megawatt. So now, first of all, we optimize optimize for the losses. Here you can see we now don't have any concern with the cost or the voltages. So first time here we'll optimize it for the losses. You can see this is the first value that is much reduced than the previous cases, 7.15 megawatt. In base case it is 13.52. So for the first time we get uh, the, mo the most reduced value here for the losses. So now the current might be increased or the voltage might not be that much improved, but we don't have any concern. We just give command for the losses only, which shows quite impressive result here. You can see. And then again, now in this case, we actually try to only optimize for the voltages. Now we don't have any concern in this case with the total losses or the cost. You can see the voltages are much improved in the previous cases from bus 1 to 30 buses. The voltages have been improved here. Now we give equal weight to each of the means cost. We give equal weight one losses and voltages. So when we give equal weight to the cost, losses and voltage, you can see the result. The cost is now 840.69 dollar per hour. In base cases in 914.36 dollar per hour. Losses are also reduced to 8.01 megawatt. You can see the voltages also here, and they are much more improved than the base case. After that, we prioritize the cost. Means we give the 50% weightage to the cost. We give weightage to the cost. That means we want cost more in our system that to reduce. So you can see here the result. The cost is reduced to 808.82 when we gave the weightage more than the losses and voltage. So this cost is much more reduced than the previous cases. You can compare here. 808 is comparatively less than the base case, also the in the previous case, because here we give the more weightage to the cost. So again we give the priority to the losses. Here you can see we gave the losses 0.50 means 50% weightage to the losses. Now we can say that this system, this program will reduce the sorry reduce the total losses, which actually you can see that base case losses are 13.52. It's now reduced to 7.53 megawatt. So this shows that the means the weightage is working actually, because first we gave the weightage to cost, it reduces cost, and then we gave the weightage to losses, means we prioritize the losses to me giving more weightage than cost and voltages. So the third time, here you can see we prioritize the voltages. So these voltages are much more improved than the previous cases. You can see here in the figure. Actually we give the weightage to the voltages here. 0.5 means 50% weightage to the voltages. Now we gave the command that we need voltages more to be improved for our power system. So first of all, what we did, we prioritized the cost, and it actually gives the best value, optimized value, and then we prioritize the for the losses, and then for the voltages. So in conclusion, our system in a 30 bus bar system, we can say that first we can improve the voltages by DG. You can place the DG on different location, so your voltages will be improved, cost will be reduced, and also the losses will be reduced. Then we move further for the wattage. We first gave the equal wattage to each of them. Then we gave the then we prioritize the cost, and then we prioritize for the losses, and then we prioritize the voltages. Means we gave the wattage for every quantity. So these are the references. Thank you so much. Thank you so much for listening.